All right, next up we have thermochemical equations. A thermochemical equation is just a regular chemical equation for a reaction. The difference though being that the energy that's involved in the reaction is somehow shown in the equation, as we'll see in a little bit. So uh, keep this in mind. In balanced thermochemical equations, the coefficients refer to the number of moles of reactants and products involved in the reaction. Now, this is always true, but sometimes we can interpret the coefficients as the number of particles, and we can't do so in this case. So the coefficients represents the moles of each of the substances involved in the reaction, and not the number of particles. Consequently, it is acceptable to balance equations then using fractions when appropriate. So you can't have a half of an oxygen molecule, but you can have a half a mole of oxygen molecules. So sometimes we'll be balancing thermochemical equations by using fractions. So we can only do so if we interpret those fractions as moles. Letter B, the numerical value of the delta H, the heat of reaction, we call that. If we're talking about the energy involved in a chemical reaction, it's called heat of reaction, delta H Rxn. So sometimes we write that as, generically, heat of reaction could be a combustion reaction. In that case, we call it heat of combustion. But we've seen lots of delta H's. So the numerical value for heat of reaction is specific to the number of moles of reactants and products specified by the balanced equation. Now this will be extremely important, and we'll touch on that more later on. When writing thermochemical equations, make sure to include the state of matter of each of the substances involved in the equation, because that has some importance as well. All right, something else to keep in mind is that though delta H may change with changes in temperature, we're going to say that the value of delta H does not change significantly with modest changes in temperature. So just assume that delta H for a reaction is a constant regardless of the temperature that that reaction occurs at. All right, there's two ways of writing thermochemical equations. One way is to include the energy associated with the reaction as a delta H value. The other way is to include the heat term, it's called, the energy involved in the reaction, in the equation itself. So let's start with exothermic reactions. A thermochemical equation for an exothermic reaction would look like this. You have the reactants on the left side, of course, products on the right side, and then off to the right, you'll be given the energy released by the reaction as a delta H value. Now keep in mind, very, very important, if the reaction is exothermic, we need to put a negative in front of that number. That negative, it's not negative energy, that negative means that energy is released during the reaction. Now, technically too, it's kilojoules of energy released per mole of reaction. I'll explain more of what that means in a little bit. The other way is to include the heat term in the equation itself. So if it's an exothermic reaction, the heat term is going to go on the right side of the equation with the products. So it'll be some number, 100, 800, 250 kilojoules, whatever it is, that number of kilojoules will go on the right side of the equation. We don't put minus the number. We just put that number on the right side of the equation. The right side tells us exothermic. The negative here tells us exothermic. If the reaction is endothermic, again, we got reactants on the left, products on the right. Our delta H is going to have a positive value. Sometimes students ask, do I need to put the plus in front of the number? I like to put it there just to make sure that I have accounted for the fact that the reaction is endothermic. The other way is to put the heat term in the equation. If it's endothermic, then the heat term is going to go on the left side with the reactants. All right, let's take a look at some examples. First on 554, example 15.3. says when 2.61 grams of dimethyl ether is burned at constant pressure, 82.5 kilojoules of heat is given off. Find the delta H for the reaction. Now, again, keep in mind, delta H is always in kilojoules per mole of something. And as we mentioned in one of the problems yesterday, per mole of the limiting reactants. So we're only given the mass of one of the reactants, so we'll assume that that is the limiting reactant. And so what we're going to do is to calculate delta H, we're going to take the total. How about this? Let me ask this. True or false? This reaction always releases 82.5 kilojoules of energy. True or false? That is not true. So how much energy a reaction releases depends on how much of the reactants react. So let's say instead of 2.61 grams, what if it was 10 grams of dimethyl ether? How much energy would be released? Well, the more dimethyl ether that burns, the more total energy is released. So just keep that in mind. Delta H, though, for a reaction is a constant because it's the energy release relative to the amount of the substance that reacts. So take a look at the setup. I don't really like how the book shows it. What I would do is I would take 82.5 kilojoules. In fact, I'll just do it here. 82.5 kilojoules. Take that and divide it by moles. So we take the 2.61 grams of dimethyl ether and convert that to moles. And that will give you your answer. Now, again, be careful. When you get this on the calculator, your calculator is going to say 1,450. This reaction is exothermic. How do you know? A couple ways. One, it tells you that heat is given off. Something else that we know is that this is a combustion reaction. All combustion reactions are exothermic, and so we have to indicate that with a delta H that is negative. So negative 1,450 kilojoules per mole of reaction. In this reaction, there's 1 mole of dimethyl ether. So it could also be per 1 mole of dimethyl ether. This also is the energy released per 3 moles of oxygen that reacts. So this number here, 1,450 kilojoules, is relative to the amounts of each of these substances involved in the reaction. Meaning, what if, how much energy is released if 2 moles of carbon dioxide is produced? Well, 1,450 kilojoules. 1,450 kilojoules of energy is released per 3 moles of water vapor that forms. Or it says liquid water, but water that forms. So keep that in mind. This is a constant. So relative to the moles of reaction that are involved in the reaction. All right, go ahead and take a look on page 595. Practice problem or exercise rather, number 21. Go ahead and set that up. Pause the video now. All right, here's our setups. 750 or 0.750 kilojoules of energy is released. And so that's when 0.100 grams of that substance reacts, methyl hydrazine. And so we take total energy released divided by moles of the limiting reactant. And since this reaction is exothermic, we get negative 345 kilojoules per mole, or per mole of reaction. Either way is fine. Letter B, what if 87.5 grams of nitrogen was produced? How much energy would be released? So again, this here is relative to the amounts of each of the substances involved in the reaction. So we're going to use the delta H as a conversion factor, a way of converting between moles and kilojoules. So first thing is take the grams of nitrogen, convert to moles, And then use our delta H. Notice what I did here, 345 kilojoules per 9/4 moles of nitrogen. That's according to the chemical equation. So just be careful with that calculation, be mindful of that. All right, 555, let's take a look there. And 15.4 just wants you to write the thermochemical equation for the reaction that occurred in example 15.2. So you have copper 2 sulfate, sodium hydroxide reacting, regular chemical equation. It was determined that the delta H for this reaction was negative 56.4. So we include that as a delta H value after the equation. All right, 65B, I actually already assigned, but review that problem. So once again, we are given, or we calculated the energy released by the reaction, and then we take that energy and divide it by moles of the limiting reactant. So we have a limiting reactant situation, so make sure to always divide by moles of the limiting reactant. All right, 15.5 on that same page, take a look. Read along. It says, when aluminum metal is exposed to atmospheric oxygen, it is oxidized to form aluminum oxide. How much heat is released by the complete oxidation of 24.2 grams of aluminum at 25 degrees Celsius in 1 atmosphere? Thermochemical equation is given to you. So very similar to what we did in 21B. So if you turn the page and look at the solution, first thing we need to do is take the grams of aluminum, convert that to moles. Notice that the book sets it up a little bit differently. So they get in their second conversion factor, they're going to convert from moles of aluminum to moles of reaction. So mole of reaction is just according to the chemical equation. For every 1 mole of reaction, according to the equation, there are 4 moles of aluminum that react. And then they do the delta H. You don't need the negative there. Back to, I showed you in my last example, I did not include the negative in my conversion factor. So 3,352 kilojoules per 1 mole of reaction, and you get your answer. So I've just take the second and third conversion factor and combine those. You get 3,352 kilojoules per 4 moles of aluminum, and you don't have to then go through moles of reaction. All right, number 17, 594, give that a shot. So there's a setup, 368 kilojoules per 2 moles of sodium, and 20.8 kilojoules of energy is liberated. That word liberated also means released. So it's given off, and that's what you get for that answer. All right, next up, we have standard states and standard enthalpy changes. Standard states or standard state conditions. Standard states, these are the conditions that the reaction takes place. Sorry, the conditions that a reaction takes place in affect the values of delta H. And so we're going to talk a lot about reactions that occur at standard conditions. Standard conditions are 1.00 atmospheres, 25 degrees Celsius, so be careful, don't confuse standard conditions with standard temperature and pressure. 25 degrees Celsius, not 0, or 298 Kelvin. And then for any solutions, concentration 1 molar. So something else that'll be important is standard states. That refers to the state of matter of a substance at standard conditions. For example, what is the standard state of oxygen? Meaning, what state of matter is oxygen at 1 atmosphere and 25 degrees Celsius? Oxygen, of course, is a gas. So that's what standard states means. A symbol for standard enthalpy change for a reaction or heat of reaction. Again, we can put that there. This little knot or degree symbol means standard conditions, 25 degrees Celsius, 1 atmosphere of pressure. All right, let's look at a specific delta H, standard molar enthalpy of formation, aka heat of formation, delta HF. Formation, delta HF, or heat of formation. The delta H for the formation of 1 mole of a substance from its elements in their standard states. What is another name for a formation reaction? Look at the definition there of heat of formation. Forming a substance from its elements. We're talking about synthesis reactions. So heat of formation, the energy absorbed or released during the formation of 1 mole. That's what's important here. 1 mole of a compound from its elements in their standard state. So I already wrote it up on the board, but here it is again. A symbol for standard heat of formation, delta HF, for formation specifically. And then that, of course, means at standard conditions. All right, take a look at 15.6 on page 557 and read along with me. It says the standard molar enthalpy of formation of ethanol is negative 277.7 kilojoules per mole. Write the thermochemical equation for the reaction for which the heat of reaction is negative 277.7 kilojoules per mole. Go ahead and turn the page and take a look at the solution. So you are producing, again, synthesis reaction, you're making, in this case, ethanol. And so the reactants are the elements that combine to make this. So we have carbon, we have hydrogen, and we have oxygen. Keep in mind that hydrogen is diatomic, as is oxygen. And when you balance this equation, you need to do so in a way that the coefficient of the compound is 1. Remember, that heat of formation is per 1 mole of the compound, so you have to adjust everything else accordingly. So that gets a 2. The hydrogen, there's 6 hydrogens on the right, so we'll put a 3 there. 1 oxygen on the right, and so we're going to put a 1/2. And so that equation as written, delta H, negative 277.7 kilojoules per mole. Now there's an appendix in the back of the book that has all kinds of heats of formation for different substances. There's a small table in your book, but if there's something that's not in that table that you're looking for, go to the appendix in the back of the book and find heat of formation. There's lots of other thermodynamic data in that table that we'll use later on as well, but heat of formation, delta HFs are there. All right, so let's do one last thing. Take a look at page 595, number 29. Basically, what it wants you to do here is to write the balanced thermochemical equations for the formation of 1 mole of each of those substances. So let's do this. Let's just do A, C, and E. I don't think we need to do all of them. If you want to do all of them, that's fine, but I'm going to show you just the answers for A, C, and E. So again, make sure to balance, as I mentioned in the last example. We're writing thermochemical equations, so you need the back of the book to find the delta HFs for each of those substances. Go ahead and do that now. Pause the video, please. All right, here's what you get. Notice for letter C, we're not forming a compound, but rather individual oxygen atoms. Formation of a substance from elements in their standard states. We don't find oxygen as just individual oxygen atoms, so we start with O2, gaseous O2 molecules. And so here are all of your delta HFs. How about this? What is the delta H for the, not formation of hydrogen peroxide, but decomposition of hydrogen peroxide? I'm not talking about decomposition, decomposing to water and oxygen, but decomposing to hydrogen gas and oxygen gas. Well, if the formation of hydrogen peroxide is exothermic, what do you think about the decomposition of hydrogen peroxide? Decomposition, which is the opposite of synthesis or formation. So if the formation is exothermic, the decomposition, I'm guessing, is endothermic. How much? Delta H, positive 187.8 kilojoules per mole. So keep that in mind. That'll be something that's important in our next lesson. The heat of decomposition, if you will, energy absorbed or released during the decomposition of a compound into its elements. All right, that's it for today. Thanks for watching.